Jnanam Paramam Dheyam. Knowledge is supreme.
So in the last lecture we saw that every field has an algebraic closure. Now the question is how many? So now we prove sort of uniqueness. It's not unique, but it's unique up to and k isomorphism. So let me state it precisely, then we will prove it. So theorem. This was also Steinitz. Let K be a field. Then 1 let E over K be a field extension with E algebraically closed in the last lecture we indicated that how to construct such a E. Okay. Then and let L over K be an algebraic extension, may not be finite. Then there exists an K embedding from L to E sigma. K embedding means, see, this is an algebraic extension, this is contained here. So we can extend this sigma is K linear, and embedding means it's a field homomorphism. So such an embedding exists for every algebraic extension. That is part 1. And part 2, which says that 2, if E and E prime are two algebraic closures of K, then there exists a K isomorphism sigma from E to E prime. That means this commutes with its K linear and it's a field homomorphism. So that means the sigma is indeed an element in home KLG E prime. It's a K algebra homomorphism from E to E prime, which is also K linear. That means K algebra homomorphism. So that means that E and E prime are unique up to this K algebra isomorphism. So let us prove this. So proof, again proof will involve John's lemma. So proof, all these theorems one cannot prove without using the John's lemma. So consider the set M. This is the set M of all pairs M comma sigma such that M is an intermediary field of L and K, and the sigma is the K embedding from M to E, K embedding. That is, it's an element in home, KALG, M to E. This is our set M. Remember, what we want to do is the following. Let me draw a diagram. L over K, this is the given algebraic extension. And we have given E. E is given here. E is contain this K is a field extension of K, and this E is algebraically close. That is what we have given. And we want to extend it here. This sigma we are looking for. K algebra homomorphism or K embedding. This is what we are looking for. So now what we have done is, we have taken all the intermediary field M's which have the extension, and we are going to maximize it, and we will prove that this process will reach M. And precisely, that means choosing a maximal element. And choosing a maximal element, one needs to apply Zorn's lemma, and one has to have an order, and we have to check that the ordered set is inductively ordered. That means every chain has an upper bound there. And one notes that there are maximal elements, and that maximal element will give us a required thing. This also shows that this process is not very natural, and this may not, the embedding may not be unique. There may be many embeddings. That's it. So let us now justify that we can apply Zorn's lemma to this set M that we have defined. So we need an order first. So define. So this set M is ordered by the following order. So take two elements in M. One is M sigma, the other is M prime sigma, and then we say that this is bigger or equal to this if and only if, this is the definition. This is if and only if M is contained in M prime and sigma prime restricted to M equal to sigma. So with this, we need to check now that this M is inductively ordered. So first of all, this M is non-empty because this K, comma, then there is a natural inclusion iota from K to L, because this L is given to be extension of K, so there is a natural inclusion. So this pair belongs to this M. Therefore M is non-empty, and inductively ordered means that is every chain. What is the chain? Chain is a totally ordered subset. Has an upper bound in M. This is what we want to check. All right. So let us call that chain to be C. So the C is the pairs Mi sigma I in I. So this I is totally ordered, and we want to check that it has an upper bound. And obviously what we will claim is, you take the union of these mi's I in I. This is, let us call this as L0. So first of all, note that this is a field. This is a subfield of, so note that L0 is a field and L0 is in between. K contained in L0 contained in L. So field is clear because if you take two elements here, both of them will lie in some Mi. One will lie in Mi, the other will lie in Mj, but I is totally ordered, therefore I can assume both lie in the same. But all these Mi's there is a field, therefore this is a field, this is clear. Another thing is, we also can extend that, you can extend that the sigma is will define sigma naught from L to E, L naught to E. How do we define this? Take any x in L naught and choose I so that x belong to that Mi, I in I, and now define, we have already given the sigma is, so define sigma naught of x to be equal to sigma of x. But this will not depend on the choice of this I, because this is a chain. That means Mi, sigma, I, and if it were in Mj, J in J, and if you assume this I is totally ordered, therefore if J is bigger, then Mi, Mj, sigma J, this is contained here, and then therefore this is also equal to sigma J. So it's well defined, is no problem. And remember, everywhere we are choosing that this is a chain. Therefore, anyway, we have therefore caught hold of this element L naught sigma naught. This is again in M, and which is clearly upper bound for the chain Mi sigma I. And now we will claim that this L naught equal to L. We want to claim this is equality here. This is what we will prove. Alright, so suppose on the contrary L naught is not full L. Suppose L naught is properly contained in L. Then what can we do? We can choose an element which is not in L naught and but which is in L. So choose x in L which is not in L naught. And remember, this L is L over K is algebraic. That is given to us, and this x is given there in L. So therefore, minimal polynomial of x over K makes sense. This is the minimal polynomial of x over K. This is not over K, over L naught. This is a polynomial in L naught x. X L over K is algebraic. Therefore, L over L naught is also algebraic because L naught contains K, and therefore minimal polynomial makes sense, and it's a polynomial in L naught. L naught is a polynomial in L naught x. So look here, this is L, this is L naught x. This is a simple extension of L naught which is contained in L. This is L naught here and this is K here, and we have an embedding here to E. And we are looking for a contradiction now. This is proper. Anyway, so therefore this polynomial is in L naught over K, and we have L naught to E, there is an extension, this is sigma naught. So therefore, this L naught, this is E is algebraically closed, and this L naught is contained in this. So therefore, I can always find, if I take the image of this, if I look at the mu x L naught and apply sigma to this, sigma naught to this, so you get a polynomial in E, this is a polynomial in Ex. And E is algebraically closed. Therefore, this polynomial will have 0. So therefore, I can always extend. So this polynomial has a 0. So y is a 0 of sigma naught of mu x L naught. So I have this, the image of this. So let me identify. So we don't have to keep saying this one. Or we have this sigma naught of L. This is a subfield here, which is the image of this, and to this I adjoin Y. So then these two fields are isomorphic. That is just given by the sigma naught. This is subfield here. So therefore, if I take this composition with this, that will give me an extension, that will give me an embedding. Let's call this embedding as, this is an embedding. So let us call this as rho. Therefore, I got an embedding rho from L naught x, this field, to E. And obviously, rho restricted to L naught is the given sigma naught. Therefore, what we check that this pair L naught sigma naught, this pair, and L naught x, this rho, this pair, obviously this is strictly bigger. This is strictly bigger. This is also in M, but this was a maximal element in M. So a contradiction to the maximality of L0 sigma 0. So this proves that L naught has to be L. This is K, this, and then that sigma naught is an embedding in E. So therefore we have an embedding of, this is K embedding. So there is a K embedding, so that this diagram is commutative. So that proves the first part. So this proves 1. All right. So now we have to prove 2. I just wanted to show you 2 is, if E and E prime are two algebraic closures of K, then there exists a K isomorphism such that E to E prime, this is a K algebra isomorphism from E to E prime. All right. So we have given two algebraic closures, E over K and E prime over K. They are algebraic closures of K. So that means two things, no? That is, E over K is algebraic and E is algebraically closed. This means algebraic closure. So similarly for E prime. Okay, so the part 1 shows that I am going to apply it to E. So applying 1 to algebraic extension E over K. Now I am looking at E over K as algebraic extension, and I am looking at E prime as algebraically closed field, and I want to apply 1. So that will tell us E here, this is algebraic extension of K, and this is algebraic closure. So this is algebraically closed field, algebraically closed. So I can extend this to embedding, sigma K embedding. This is by part 1. Now I want to show that this sigma is indeed an isomorphism. This is an embedding, and now therefore E, if I take the algebraic closure of, let the algebraic closure of K this way. of E of K in E prime. Why this? So let me write on the next page. So we have this diagram. So E to sigma, E to E prime, we have the sigma. I want to show the sigma is an isomorphism. So look at sigma of E. See, it's a field, therefore I only have to check it is surjective. So this is the image of sigma and this one. Now the sigma E is algebraically closed. E is algebraically closed, therefore sigma E is also algebraically closed. This is also algebraically closed. And these all this contains K. This is algebraic extension. So if I take this field and take its algebraic closure in E prime, so algebraic closure of sigma E in E prime. Algebraic closure of sigma E is also algebraically closed. And this is contained in E prime. It contains K. So, but this is algebraic closure. So that will show that this is equality here. So therefore, we note that sigma E is E prime. That means this sigma is surjective. And that means it's a K isomorphism. That is what we wanted to prove. Alright. Now, I want to make two remarks. Two very important remarks. One, this K isomorphism sigma in 1. Remember that is L over K algebraic. This is algebraic and this is algebraically closed field. E is algebraically closed. And then we have extended this here. This sigma, which is a K embedding. This is not unique in general, as I remarked earlier also. So therefore, in 2 also, the K isomorphism in 2, that is also not unique. Because all these we got by using Zorn's lemma and by choosing a maximal element, and partially ordered set may have more than one maximal element. So therefore, it's not unique in general unless E equal to K. Anyway, but if you don't have this, that means if your field is not algebraically closed, then the algebraic closures of K are not unique in general. Unless K is algebraically closed. So therefore, we cannot say the. We are not allowed to say the. So we will keep saying an algebraic closure. That is one remark. This is very, very important because one may get a feeling that these are unique. Okay, the next remark 2. If I want to study algebraic, so study of algebraic extensions of a field, this study this study we will reduce it to, if I choose E over K algebraic closure of K, an algebraic closure. So choose an algebraic closure of K that we know it exists now, and then this, therefore f of intermediary field of E over K makes sense. See, this is the set of intermediary subfields in between E and K. So, if you want to study algebraic extension of this, it's enough to study this. Study of algebraic extension of a field K can be reduced to the study of the set E over K of intermediary subfields of E over K, where we have chosen an algebraic closure of K. So, this I have not used earlier, but this is very important in the study of this. Okay, now the next one is, so I would rather stop here and prepare for proving that the field of complex numbers is algebraically closed. And for that proof, I am going to use the fundamental theorem on symmetric polynomials. This I will do it in the next lecture. Thank you.